Hi friends, here is a quite involving question about gas processes. This one is also involving thermal energy, so we will be practicing that with this question as well. It's not a big stretch from what we practiced before. We have a cylinder with a movable piston that contains 0.016 mole of helium. So let's put the mole here. And a 0.016 mole. A researcher expands the gas via process illustrated in the figure below. We have a PV diagram here. This is the direction of motion. As we all know, we go along the direction of arrow. So we have an initial pressure 400 kilopascal. Make sure you read the unit also here. It could be pascal, kilopascal. And initial volume is at 100 centimeter cube. And then we expand it. Final volume, this would be our V initial. This would be our P initial. This would be our V final. And this would be our P final. Excuse me. Okay. So apparently the gas is expanding. We have a larger V final. To achieve this, does she need to heat the gas? Yes, she does. It's expanding. That means particles are moving faster and faster. So she needs to heat the gas. If you heat the gas, there will be a thermal energy change. And we can calculate this delta E thermal using 3/2 nR delta T. Remember, E thermal is defined as 3/2 nRT. If I find the change in thermal energy, we can just multiply that by change in T. Delta E thermal would be E thermal final minus E thermal initial, not equal, minus. And that would be equal to this value here. So I did some thinking here. If she should heat it, this much thermal energy should be given to it. To achieve this, does she need to heat the gas? Yes. If so, how much energy, heat energy, must be added or removed? This much energy added. So this must be added. And if I write this out, write this delta E thermal out, I will have 3/2 nR T final minus T initial. So if I know T final and T initial, I will be able to calculate that. Remember, here R is the gas constant. Well, let's put that over here. I'm going to take that away. And it's equal to 8.31 mole per Kelvin. How do we find T initial, T final? Is using gas processes from here. We don't know any of them. We know P initial, V initial, P final, V final, and we can reach T initial, T final using these information. First of all, I can apply ideal gas law, PV equals nRT, to find either one. So I'll have P initial, V initial equals nRT initial, and solve for T initial. T initial from here will be dividing each side by nR. I'll leave it alone. P initial, V initial divided by nR. I know everything. I can solve for T initial easily. My P initial is 400 kilopascal. That would be 400 times 1000, 10 to the 3 Pascal. We initially is 100 centimeter cube. That would be 100 times 10 to minus 6 meter cube. That's how we always convert from centimeter cube to meter cube. Divided by N, 0.016 moles, times R, 8.31 mole per Kelvin. And if I do that, I'll have T initial as 300.84 Kelvin. Now go ahead and do the same for T final. With the same approach, we will have P final, V final equals N R T final. Solve for T final. Let me divide this here. T final will be equal to P final, V final divided by NR. Put in the value. You'll read V final from here, 300 centimeter cube, P final 200 kilopascal, and you'll find your T final as 451.26 Kelvin. And you will insert these guys here. Everything else is known. So delta E thermal, which is the heat energy she should give, she should give to the system, 3/2. N is 0.016 again moles. R is 8.31. I drop the units here and I enter my T final, 451.26 Kelvin minus T initial, 300.84 Kelvin. Let's drop the Kelvin here as well. So I use the appropriate units. So I'm going to find my heat energy in joules, and the answer should be 30 joules. Make sure you solve all this and find this result here.